This research explores the development of large neural video coding models, focusing on scaling up model sizes and architectures to enhance video compression performance. Inspired by the success of large language models and large vision models, the authors propose a large neural video coding model, NVC-1B, with over 1 billion parameters. NVC-1B is based on the small baseline model DCVC-SDD, which has higher compression performance than H266, VVC under certain conditions. The authors analyze the influence of model sizes on compression performance by scaling up different parts of a neural video coding model, including motion encoder-decoder, motion entropy model, contextual encoder-decoder, and contextual entropy model. They also explore different architectures, such as CNN, mixed CNN transformer, and transformer architectures. The results show that scaling up the model size and changing the model architecture can significantly improve video compression performance. The NVC-1B model consists of key components, including motion estimation, motion encoder-decoder, temporal context mining, contextual encoder-decoder, and entropy models. The authors provide an overview of the NVC-1B framework, detailing the process from motion estimation to contextual encoding and decoding. Experimental results indicate that scaling up the model size of the contextual encoder-decoder and contextual entropy model consistently improves compression performance, while scaling up the motion encoder-decoder and motion entropy model may not always result in better performance. The authors observe that larger models may lead to training instability and reduced performance gains. However, the proposed NVC-1B model achieves state-of-the-art compression efficiency, suggesting that large models may bring video coding technologies to the next level. The findings of this research highlight the importance of exploring the influence of model size on compression performance in neural video coding models. This study investigates the impact of scaling up model size and modifying the architecture of a neural video coding model. The authors examine the effect of increasing the model size of various components, including the contextual encoder-decoder, contextual entropy model, and temporal context mining module, showing that scaling up these components can lead to significant compression performance improvements. For instance, increasing the model size of the contextual entropy model from 90 m to 212 m yields an additional 0.8% performance gain for the HEVC Class C dataset. The study also explores the influence of model architecture, specifically the mixed CNN transformer and transformer architectures. The authors build models incorporating SWIN transformer layers into the contextual encoder-decoder, contextual entropy model, and temporal context mining module, respectively, showing that the mixed CNN transformer architecture can bring performance gains, but the CNN architecture counterparts achieve higher video coding performance gains. However, inserting SWIN transformer layers into the temporal context mining module results in performance loss. The transformer architecture is also investigated, replacing convolutional layers and residual blocks with SWIN transformer layers, showing that the transformer-based contextual encoder-decoder can bring a small performance gain, but the transform-only based contextual entropy model and temporal context mining module lead to model crashes. Based on these findings, the authors build a large neural video coding model, NVC-1B, with a CNN architecture, allocating most of the model parameters to the contextual encoder-decoder, contextual entropy model, and temporal context mining module. The model is trained using an elaborate strategy, with 6 training stages classified according to the training loss functions. The NVC-1B model significantly outperforms its small baseline model and state-of-the-art neural video coding models, achieving an average 25.1% bit rate reduction over VTM 13.2 across all test datasets, making it a promising solution for neural video coding. The proposed large neural video coding model, NVC-1B, demonstrates significant performance gains over traditional video codecs and state-of-the-art models, such as ECM, in terms of YUVPSNR and bit rate reduction. Evaluations on various video datasets, including HEVC Class B, C, D, and E, as well as UVG and MCLJCV, show that NVC-1B achieves an average bit rate reduction of 20.5% compared to VTM. Subjective comparison results reveal that NVC-1B can retain more textures with a lower bitrate than its small baseline model, DCV-CSDD. The analysis of transform energy compaction demonstrates that NVC-1B can effectively compact the energy of the contextual latent representation, leading to improved compression performance. The average contextual bitrate ratio of each channel is calculated using equation 7, and the top 100 channels with obvious energy compaction are presented. The results show that NVC-1B can efficiently allocate bits to the most important channels. The performance gain of NVC-1B is mainly attributed to its ability to use more frames for multi-frame cascaded fine-tuning. However, the number of frames used is limited by the GPU CUDA memory. Increasing the model size of the motion encoder-decoder can lead to performance gains, but the gain decreases if the model size is continuously increased. The results also show that NVC-1B has higher transform energy compaction and more concentrated motion channel bitrate distribution, indicating that more signal energy is concentrated in fewer channels, which is beneficial for entropy coding. The analysis highlights the importance of considering both model size and architecture in neural video coding. Future work should focus on designing larger models with more efficient architectures to further improve video compression performance.